Ever wondered how nuclear reactors generate electricity? Let's dive into the fascinating world of nuclear energy. To truly grasp the intricacies of nuclear reactors, let's delve into the critical role played by uranium-235. This isotope is the key to initiating a chain reaction, a process better known as nuclear fission. It's the heart of the reactor where the magic of energy release unfolds. When a uranium-235 nucleus captures a neutron, it undergoes a transformation, becoming highly unstable. This instability causes the nucleus to divide, forming two smaller nuclei, such as krypton and barium. This fission process not only produces additional neutrons, typically 2 or 3, but also releases a considerable amount of energy. The neutrons that emerge from this reaction have the potential to interact with other uranium-235 nuclei, perpetuating a self-sustaining series of reactions known as a chain reaction. Uranium occurs naturally as a mixture of isotopes, but only uranium-235 possesses the remarkable ability to sustain a chain reaction. Unlike its more abundant counterparts, uranium-238 and uranium-234, uranium-235 undergoes fission when bombarded by slow-moving neutrons. A nuclear reactor is a complex system designed to harness the energy released during nuclear fission. Let's take a closer look with a cross-sectional view. The reactor vessel, made of heavy-duty steel, encloses the core and withstands high pressure, preventing radiation from escaping and ensuring safe operation. Inside the reactor vessel is the core, the epicenter of nuclear reactions. This core contains fuel rods, control rods, and the moderator, all essential for the fission process. Fuel rods, usually made of enriched uranium or plutonium, are crucial for initiating and sustaining fission. Each fuel rod is filled with numerous fuel pellets, small cylindrical pieces made of uranium dioxide, UO2. A typical pressurized water reactor, PWR fuel assembly, contains 179 to 264 rods with a diameter of approximately 20 centimeters. These rods are structurally supported to withstand the extreme thermal and strain stresses within the reactor core, ensuring they do not displace. Control rods, made of materials like boron or cadmium, absorb excess neutrons and regulate the chain reaction. By adjusting their position, operators can control the fission rate and maintain stable power output. Sustaining a chain reaction is complex. Neutrons from fission move at high speeds, making further fission less likely. This is where the moderator, often water, comes in. It slows down neutrons, increasing their chances of causing more fission reactions. Now, let's see how all these components work together in a nuclear reactor. Fuel rods containing enriched uranium are placed in the reactor core. Neutrons from fission collide with other uranium nuclei, causing them to split and release energy. Control rods are adjusted to regulate the fission rate and maintain steady power. The moderator slows down neutrons, increasing the likelihood of further fission reactions. The heat from fission warms water around the fuel rods. In pressurized water reactors, PWRs, this water is kept under high pressure to prevent boiling. In boiling water reactors, BWRs, the water boils. The heated water is then pumped out of the reactor core and into a steam generator. Here, the heat is transferred to a secondary water system, turning it into steam, while the now cooled primary water is pumped back into the reactor core to be reheated. The steam, whether directly in a BWR or via a steam generator in a PWR, spins a turbine connected to a generator. As it turns, mechanical energy is converted into electrical energy. The heat generated from fission is used to produce steam, driving turbines connected to generators, ultimately producing electricity. The heat from fission turns water into steam, which spins turbines to drive generators and produce electricity. And that's how a nuclear reactor works. It's a complex blend of physics and engineering, ensuring a steady supply of clean energy. Thanks for joining us on this atomic adventure. If you're eager to learn more and join a community that shares your passion for discovery, like this video, comment with your insights, and most importantly, subscribe to Curious Cube.